Welcome back, everybody, and hello. I'm Mikko Koivisto. I'm going to chair this session. So this is the last plenary session of the main conference. So we're going to have two presentations here physically. The two other presentations assigned to this session are available online as recorded video recordings. So please check out. I think our first speakers are ready. So we have Neil Adai and Lingshu Yang, and they will tell us how Gaussian process limit reveals structural benefits of graph transformers. Please go ahead.
Okay. Good afternoon, everyone. My name is Lingshu Yang from the University of Tokyo. And today, I will present our work, Gaussian process limit reveals structural benefits of graph transformers, joint work with Neil Adai and Professor Gaussian. And since they already have many theoretically analyzed of traditional graph neural networks, but still lack of work doing some analysis based on graph transformers, so which is harder. And our goal is to understand graph transformers theoretically through their Gaussian process limits. First, let me briefly introduce the data setup about a graph. And the graph consists of nodes and edges, and each node has its own feature vectors. And we connect the node features into the feature matrix X, while the graph community is represented by the adjacent matrix A. And so essentially, we have these two sources of information, nodes and node features and the graph structures. And to talk about the graph neural networks. A graph neural network combines these two information through the message passing, as shown in these kinds of figures. Each node starts with its own feature, but it can also receive information from connecting nodes. And more specifically, each node collects the representation of its neighbors and combines them into a new representation. So the graph structure directly determines how information is propagated locally. Now we write the update more formally, and the S represents the graph convolution, which aggregates information from the neighboring nodes and according to the graph structure. And by considering graph convolution network, the S matrix is adjacent matrix, and Y applied a weight matrix to obtain the pro-activation graph convolution network before the nonunity activation functions. And here we show the complete graph neural network layer by adding the nonunity function. This produces the hidden node representations shown in the middle of these figures. And for deeper graph neural network, we simply repeat the same operations. And the hidden representations from one layer become the input of the next layer, so the information repeats perfectly through the graph, and the final output is on the last layer. So let's talk about the infinite width limit of the graph convolution network by make the hidden layers to be infinite width. By consider for the graph convolution network, when we consider these Gaussian distribution initialized weights, and when the hidden width becomes very large, the pre-activation will converge to a Gaussian process with kernel sigma shown in this formula. And we can also get the kernels for the post-activations in these formulas, as we can see. And the initialized with the sigma can be computed in this in the formulas like this part. And by using these ways, instead of tracking all the individual neurons and weights, we can characterize the model through its covariance map kernels, which describe their similarities between different nodes, which can make this theoretical analysis more easily and more analyzable. And then we're transitioning to graph transformers, the graph attention network. For graph convolution, the aggregation weights are essentially fixed by the graph structures, but graph attention network instead nerd attention weights between connected nodes. So different neighbors can contribute differently depending on their representations. And practically, GATT also use multiple attention heads. As shown here, different heads compute different attention scores on the same graph, and their outputs are then combined. So for example, in these figures, the head one, in the head one, the connection between F1 and 3, there are the strong connections from F3 to F1, but the situation is totally different in head 2. So in our work, we show that GATT also converges to a Gaussian process with the limit of infinite width and infinite heads. And with that, I will hand over to Nia, who will explain this Gaussian process limit and how it leads to a Gaussian graph transformer kernels with analyzing these rest of the talks. Thanks very much.
So unlike their Gaussian graph convolution network counterparts, it's not enough to just take the width to be large for graph attention networks output to converge to Gaussian, as you see in this figure. We need both the number of heads and width to be large. And in our work, we show formally as both the channel width and number of attention heads tend to infinity, this pre-activation G converges to a Gaussian distribution with a specific kernel matrix sigma. And now I will tell you a bit about how this kernel matrix sigma is different than that of the GCN. So in GET, we not only get the node-level covariance kernel, but we also get edge-level logit kernel, so which encodes the covariance between attention score on edges. So if we have an edge between the nodes A and I, and another edge between the nodes B and J, then the covariance between these two edges will be proportional to the covariances between these nodes A and B and E and J. And later, this edge-level logit kernel gives rise to the convolution kernel, which appears in the calculation of the node-level covariance kernel. So this one encodes the attention score between these two edges, and the kernel between nodes A and B will be proportional to the covariances between the nodes E and J, where E and J are neighbors of A and B, and this attention kernel is kind of scaling so that how important is these two neighbors for these nodes. And so what we did is we write down the edge-level kernels and the node-level kernels for three graph transformers, namely GET, GraphFormer, and SpecFormer. In this talk, we will only focus on GET due to time constraints. So we have this expression for these kernels, and we need this GP equivalence to study the structural limitations of graph transformers. So for example, let's consider the oversmoothing problem into account. So oversmoothing is an inherent problem in GCNs. So we said in GCNs, so where the convolution is fixed, it kind of does an averaging of features. So in every iteration, you average the features, and if you have enough layers, at the end, all of the features will converge just to the same feature. So you kind of lose all the information. So if we have large number of layers, GCN loses all the information. And this is what we call oversmoothing. And this is a problem in GCNs. Now, there are conflicting views whether graph transformers can overcome this problem by using the attention mechanism. And we answered this question from a structural point of view using our GP kernels. To do this, we write down our GP kernels under a stochastic block model, short SBM. SBM is a random graph model where nodes are partitioned into two communities where the probability of an edge existing between the same community is P, and Q if they belong to same communities. So for example, if P is bigger than Q, then we have a homophobic graph. So nodes within the same community, like this red one, are heavily connected, and to the other community, it's sparsely connected. And if we have such a graph, we know that the adjacency matrix of this graph will have this block structure. So this block corresponds to this red community. They are heavily connected, so this one appears black, whereas the connection to the blue one is sparse. So this part appears white. So we have this block structure. But it could also be the other way around. So if you say, OK, I want a heterophilic graph, I want Q to be bigger than P, then the nodes in between communities are heavily connected and sparsely connected within. Then you still get the block structure, but it's the other way around. And the idea is the following. If a kernel method can learn this graph, then the kernel itself should also have this block structure, or else it cannot distinguish communities. So what we did is we wrote down the formula for our kernels, under this stochastic block model and look at their behavior when the number of layers goes to infinity. And so we did this theoretically, but I will now show you some experimental plots to make the point more clear. So we have such a SPM graph, and if a kernel method is able to learn this graph, it means it should have this block structure. And if you look at GCN for one layer, like it has clearly this block structure, it learns the graph. But if you go to 10 layers, the information is completely lost. You converge to a constant kernel. Whereas if you consider get, and if the signal is strong, and what I mean by that is P divided by Q is bounded away from 1. It means like either you have a really homophobic graph, either P is bigger than Q, like clearly, or the other way around, you have a really heterophilic graph. If they're close to each other, it means it's like you don't have this clear community distinction. And if the signal is strong, even if we go to large number of layers, we still see the block structure in the kernels. So get can overcome oversmoothing under the condition of strong signal. Whereas if the signal is weak, oversmoothing still happens. So by using our GP kernels, we showed that the graph transformers can overcome the oversmoothing problem under certain conditions, which we specify in our paper. Let me also show you some real-world dataset examples. So here we did examples on a Camelon dataset, which is a benchmark heterophilic dataset, and also PubMed, which is a homophilic dataset, and we plotted the test accuracy over number of layers. The one you see in blue is the GCN GP, and as you see, the accuracy drops as you increase the number of layers. And if you look at graph transformers, they are rather high. If you look at orange, like the get GP that I have been talking about, you see that the accuracy stays pretty high. And since in this real-world dataset, there are like a clear class distinction, so the signal is quite strong. So in conclusion, we provide a unified theoretical NNGP framework for 3 graph transformers, and we wrote the GP equivalence of these graph transformers under the same framework, which we use to show some structural benefits of graph transformers over GCNs. Specifically, we focused on oversmoothing as a structural issue, but the analysis should not be limited to that. One can extend the current methods to other phenomena, such as oversquashing or heavy heteropholy. So you also see that the accuracy of our GP methods are actually rather high. So they can even serve as a standalone practical methods, given someone can come up with some scalable kernel approximation, which is not that trivial, if you want to discuss later. And lastly, I think this is really interesting. Since we not only get a node-level kernel, we also have this edge-level kernels. So we are thinking our methods can be extended to edge-level tasks, such as link prediction, which is an interesting future direction. So in general, I believe our GP framework opens the gate for a lot of interesting direction about graph transformers and investigating graph transformers theoretically. So that's all from our side. Thank you for your attention.
Thank you very much. We have plenty of time for questions. There is one person.
Thank you for the presentation. My question is on, is there any reason or intuition why the GP of the initial network, why that tells us anything about its behavior during or after training?
Yeah, this is like a good question about the GPs. So at the end of the day, GP is an approximation of what's happening in the trained neural network. And there are works that show that it's a good approximation. But it's not the exact trained neural network at the end of the day.
Yes, so about that, to my knowledge, indeed, like an NGP, or I don't know, however you call this, kernel in this case, is a good description for infinite width networks at initialization. However, during and after training or at convergence, the behavior is also, let's say, governed by the NTK. I mean, that's assuming it even holds in this case. So, I mean, so then we have to think about, okay, how does the NNGP kernel differ from the NTK, and what implications that would bring?
Okay, that's actually a professional questions about this area. So talk about, about NTK and NGP, but actually, by mathematically, if you derive these kernels, you can see that in our analyzed sections about the oversmoothing, actually they are the same. So we have already done this part, but we show only NGP, but actually in a later training, they will show the same oversmoothing characterizations in the both case. Thanks.
You mean like you show that in this?
Let's take further discussions offline. Yeah, thanks. Other questions?
Not, can we give another answer to the first question?
Okay, okay, then, yeah. Okay, keep going.
So what my colleague said is, like in this paper, we don't have the NTK kernels, but we continued working on it, and NTK show the same phenomenon in terms of oversmoothing. But also something I wanted to add is our claims are about the structural properties of these models. That's why I keep stressing the word structural. So in the case of GCN, for example, if you look at the GP kernel, it is destined to oversmooth, like even in initialization. So there's nothing you can do. What our work shows is for graph transformers, what the GP tells us is there's still hope in not oversmoothing. So it's not a structural issue. It may be according to like the training. So it's different between GCN and graph transformers.
Good, thanks. And now, more questions. Well, I have one. So your theoretical analysis is sort of asymptotic, yeah, like a limit behavior. Now, can you like analytically say something when these lengths are finite, something? Do you have some control of that?
Yes, there is some work talk about the convergence of how we can be infinite, what the behavior will be different when we from finite to infinite. So we also do some work to show that how wide this network would be. It will perform like the same to infinite. It show like maybe 1,000. The hidden layers is 1,000 width. It looks like much more like infinite thing. So the convergence is also a very interesting part of the theoretical analysis. How to converge to infinite width with this rate. Okay, thanks.
Okay, thanks. Let's thank the speakers again. Okay, and then we move to the second speaker, Colin Samplowski. The stage is yours. The title is Bayesian Adaptation Gym. There's also a longer title somewhere, but well, I'll let Colin tell you.
Okay, so thanks everyone for coming to my talk. It's really exciting to be here in Amherst with you all. And I think this is the last talk of the conference, so I guess they saved the best for last. And I'll be presenting Bayesian Adaptation Gym, which is about the Bayesian adaptation of multimodal foundation models. So I'll just give a brief introduction. I'm Colin Samplowski. I'm a computer scientist at SRI International, formerly known as Stanford Research Institute, and I work in the Neurosymbolic and Computing Intelligence group with my co-authors that I'm showing here. So to start with a high-level framing, we all know that there's these really large language models and foundation models that are being used across a lot of different domains, but we're still plagued with this question of, can we really trust the conclusions that they're giving us? And this is becoming an especially relevant question because these models are being used in really high-stakes domains like healthcare and science, and even just everyday use from the public. So there's been a lot of work looking at uncertainty quantification as one approach to improve the trustworthiness of these models. And what we do here is we try to get the model to expose how uncertain it is about a task that it's trying to solve or a question that it's trying to answer. And if this uncertainty is well calibrated, we gain some insight into how much we should trust the conclusions that the model is coming up with. And a well-principled approach to uncertainty quantification in prior work is Bayesian deep learning. In here, we try to explicitly approximate a posterior over all of the model weights W for some neural network and some data set D. So intuitively, we're trying to learn a distribution over all the possible neural networks that can fit the data set D well. And once we have this, we can compute predictive uncertainty for some input X and output Y by marginalizing over these weights. And in practice, we generally draw weight samples from the posterior to form Bayesian ensembles that approximate this intractable integral. And prior work on Bayesian deep learning has shown that it can have a number of advantages, such as these ensembles are better calibrated, we generally see improved decision-making under uncertainty, and are generally more robust to small data sets. But one of the fundamental challenges of Bayesian deep learning is that approximating this posterior scales poorly as the model size grows. And that's especially problematic now because we're dealing with models that have billions to trillions of parameters when we're looking at modern foundation models. But Bayesian deep learning isn't the only field that struggles with this. With these super large models, even fine-tuning is often intractable. So if we think about a single weight matrix in an LLM like Qwen 3 8 billion, which is honestly on the small side for current models, we'll have an n by n weight matrix W. N will be over 4,000 in this case, resulting in 16 million parameters just for a single weight matrix in this model, of which there are thousands. So it's difficult to fine-tune them because we just can't fit all of the parameters and gradients into memory during training on hardware that most people have access to. So a common approach to make this tractable is to perform low-rank adaptation, also known as LoRa. So we leave the original weights W fixed, and we learn these low-rank factors A and B, which you can think of as a low-rank update to the weights W. And these factors share a common rank R, which is typically very small, on the order of like 8 or 16, which means that these new parameters that we're learning are less than 500,000, which gives us significant savings and makes training the models, or fine-tuning the models in this case, a lot more tractable. So in the last couple of years, there's been work at merging these two separate fields where we have Bayesian LoRa. So rather than model a posterior over all of the model weights, we model a posterior over only the low-rank weight updates instead. So here I'm showing a figure from a method called Bayesian LoRa by backprop, or blob for short, where we approximate the posterior over A as a Gaussian distribution, which we can learn end-to-end using online variational inference. Then once we have this distribution, we can draw stochastic samples from it and use the original weights along with the term B to project them all the way up into the full weight space, allowing us to form Bayesian ensembles over the entire model. And this has shown some interesting results, and there's already been a large variety of approaches that have been proposed for Bayesian LoRa. So we have classic approaches like deep ensembles and Monte Carlo dropout, as well as some more recent approaches that looked at post hoc applications such as a Laplace approximation and some posterior variance calibration. But the state-of-the-art methods tend to be these online variational inference-based approaches like Blob and its various successors. And I'll give a special shout out to Scalable, which was my work from UAI last year. And after we finished that paper, we were continuing to work on this problem, and I kept on running into this issue of I would add additional complexity or try a different technique, and it was never really clear if I was really seeing improvement over the baselines. And this led me to this really large-scale benchmarking of all of the prior work on Bayesian LoRa and the data sets that were typically used in prior papers, which sort of planted the seed for what became this paper. So basically what I found is that in the prior evaluation, they typically used 6 simple text-only multiple choice trivia and common sense reasoning data sets. And what I found is that as models have gotten better, the pre-trained models already had really good performance on these data sets. So this is for Qwen 3 8 billion, And we can see that the pre-trained model before any fine-tuning already has pretty good accuracy on this data set called ARC challenge. And you can think of MLE as the base LoRa fine-tuning without any Bayesian machinery. We see a very small improvement. And what that means is that since these models are already so good, there really isn't much adaptation that really needs to be done for these particular data sets that were used in prior work. But typically, Bayesian LoRa approaches were differentiated based on how well they calibrated the final classification performance. So here on the x-axis, I'm showing Qwen3 models across a different number of sizes, and then we're looking at the expected calibration error and the NLL of the classifier for the OpenBook QA dataset. And these red bars denote the gap in performance between the non-Bayesian LoRa approaches here and the Bayesian LoRa approaches here. So we do see that there is a nice drop in calibration error when we do these Bayesian approaches, likewise with NLL. And this gap became the primary metric that was used to differentiate methods and to claim state-of-the-art. But what I found is that if you just do a simple post-hoc temperature scaling, you can be basically indistinguishable from the state-of-the-art Bayesian methods. So these lines are basically right on top of each other. And this isn't a perfectly fair comparison because the temperature scaling requires a validation set, which is extra data that the Bayesian methods don't have. But it got me afraid of this question, which is Bayesian LoRa really doing anything useful, or are we just doing a very expensive calibration procedure? And the prior evaluation setup just didn't really give us enough power to really answer this question. Because everything was just based on calibration, but temperature scaling was already doing really well in that situation. So if what you care about is calibration, why use Bayesian LoRa when you could just get a little bit of extra data and calibrate your model using temperature scaling? So in an effort to answer this question, I developed what I call Bayesian Adaptation GIM, or BAG for short. So BAG is an open source benchmark that unifies and expands the prior work on Bayesian LoRa. It provides modular implementations of the prior methods, which hopefully will support continuous integration of new data sets and methods as they become available. And it currently provides a suite of data sets. So I keep the prior text-only data sets mainly for posterity's sake, but I also expanded it to text-based mathematical and logical reasoning data sets, medical imaging, and scene understanding. So now I'll go over some brief highlights of BAG and some interesting conclusions that we found. So highlight number one is that BAG is fully multimodal. So in our paper, we expand Bayesian LoRa to visual language models for the first time. And that's pretty exciting because image-based data sets enable new out-of-distribution evaluations that weren't possible using text-based data. And this is a pretty interesting thing to study because going all the way back to the prior work on Bayesian deep learning, there's always been this promise that these Bayesian methods should be more robust to out-of-distribution data, or you should be able to, they should have higher uncertainty when we're out of distribution. So here I'm showing an example of the SLAKE data set, which is a medical imaging data set in BAG. I think this is a CT scan of a spleen, but I'm honestly not 100% sure. But we can add an arbitrary amount of Gaussian noise to study how the model responds to different out-of-distribution data. So I'll show an example of this here. So this was using this super noisy data here. And on the x-axis, we're looking at the predictive entropy of the misclassified test instances across a variety of different approaches. And on the y-axis, we're looking at the overall test set accuracy, which is about the same across all methods. And what we can see here is that the state-of-the-art Bayesian methods have higher predictive entropy when they make misclassifications compared to the pointwise LoRa methods, which have much less uncertainty. So what this means is that this sort of standard LoRa fine-tuning has the same problem that a lot of deep learning has, which is that when it makes mistakes, it's still very confident that it's correct. So although these Bayesian methods are still making mistakes, they're very uncertain about that being the true answer, which can be a useful signal when we want to know what to do with the predictions that the models are making. So highlight number two is that BAG is designed for research. So it leverages the Hydra configuration system, which makes it really easy to configure the experiments using a YAML file or command line arguments. This provides native support for the Ray distributed computing framework, which makes it really easy to perform a grid search over a lot of different hyperparameters. So a single 10-line command can kick off a grid search of hundreds of experiments. And I use this in the paper to perform a sweep of nearly 5,000 experimental runs, where we looked at things like model size and model family, the LoRa rank and the size of the test time ensemble, different data sets and modalities, and then we did everything across multiple seeds. I don't really have time to get into all those results in this talk, but in the paper there's an extensive appendix where I enumerate a lot of these different splits. So highlight number 3, which is the most exciting to me, is that BAG has support for active learning. So we actually applied Bayesian LoRa to the task of active learning for the first time. And here we start with a very small pool of 10 labeled instances, and we train a method, either base LoRa or Bayesian LoRa, using just those 10 instances. And then in the subsequent steps, we look at the uncertainty that these models have over unlabeled instances, take the points that have the highest uncertainty, and add them to the training set for future training runs. So for the base LoRa that has no Bayesian machinery, we just use the predictive entropy of the classifier. But with Bayesian LoRa, since we can form these ensembles, we perform Bayesian active learning by disagreement, also known as BALD, which looks at which picks the points that have the highest disagreement amongst the ensemble members. And what we can see is that if we use Bayesian LoRa, we're able to converge faster using less data, which suggests that Bayesian LoRa is not just a calibration procedure, it actually provides uncertainty that is useful for decision making, such as data selection. So now I'll briefly go over how to use and extend BAG. So the central software object of BAG is this monolithic trainer, which is similar to something like PyTorch Lightning. Everything is defined using this Hydra configuration file. And here I'm showing an example where we're running this train and evaluate Python script. And these are the sort of updates to the Hydra configuration that we're running from the command line. So we start by defining an LLM or VLM from Hugging Face. In this case, we're using Qwen3 VL in 3 different sizes. And since we're giving it 3 different options, that'll automatically create 3 branches in our grid search, because we're running everything in parallel over 8 GPUs. And a lot of the time, you can try a brand new LLM or VLM just by updating this line without any additional code. We then define our LoRa model, which in this case is the default with a rank of R. We then define a LoRa wrapper, which is my name for the additional logic that's being applied to the LoRa adapter, which is where the Bayesian machinery lives. So here we're using scalable, because I'm biased towards my own work, and we're going to train it with variational inference, and we're going to have a test time ensemble of 10 members. We pick a data set. In this case, we're going to do Slake, and then we can evaluate it on in-distribution or out-of-distribution data. We then get a JSON file with model accuracy, UQ metrics like ECE and NLL, as well as fine-grained resource usage. So to show an example of extending BAG, we'll look at how I implemented Monte Carlo dropout. So first, we need to extend this LoRa wrapper object. In these red boxes, I'm showing the base LoRa logic. So here we're computing the base layer. And then here's the low rank factors A and B that we can manipulate however we want. And then this one line is the additional logic that's needed for Monte Carlo dropout, which is that we apply dropout even in evaluation mode. Similarly, it's easy to add new data sets to BAG. So here I'm adding a Hugging Face data set, OpenBook QA, but it's really easy to add any data set that outputs a dictionary with prompt, label, and question ID, and optionally image. So now I'll conclude with a call for collaboration that I'm still actively developing BAG. I'm hoping to add state-of-the-art methods as they appear, hopefully with author collaboration. But I'm mostly looking for challenging tasks and data sets, which is one of the fundamental challenges of working with LLMs, is that they're just so good now that it's really hard to find tasks that they struggle with. But I'm personally hoping to extend it to long-form text generation and agentic tasks. But my poster is upstairs right after the session, so please come talk to me if you're interested in collaboration. And I'm currently on the market for postdocs. But I will just end with a QR code to the code and all of my contact details, and I'll be happy to take any questions. Thank you.
Thank you. Okay, time for questions. Here is the first one. Where's the mic? Do we have?
Thank you. It's probably a very trivial question, I just don't know. if you compute something like the NLL, do you account for semantic similarity between answers? Or really just look at the softmax probabilities and how they relate to the...
Yeah, so everything is still doing multiple choice. So the softmax will be over like A, B, C, D, E. So you just look at the softmax probability of the classification. Okay. But you definitely could. I think that would, when I try to push it towards like long form text, then those kind of questions will definitely come up.
Okay, yeah, thanks.
Hi, thanks for the nice talk.
Thank you.
I have a question about this active learning. Can you expand a bit actually what happened, what's actually the benchmark and what's going on there?
Yeah, sure. So I'm using this data set that I created called symbolic regression QA, where I randomly generated a bunch of plots. And then we asked the model, which of these formulas generated this plot. So that was the data set we were using. And we start with 10 of these labeled instances. So I can generate as many of these as I want. And I start with 10 labeled instances, and I train either LoRa or Bayesian LoRa using only those 10 instances. Then we can draw a big pile of, we know the labels, so they're unlabeled, but you can imagine that if getting the labels is really expensive, then what we care about is reducing the number of data points that we need to label. And then you just run this trained model on the unlabeled instances, and you can compute the uncertainty that the model has across all those instances. You pick, I think it was the 10 most uncertain, and then you add those to the training set, and then you retrain the model. And yeah.
Okay, I see, thanks.
More questions? Comments? There is?
Yeah, great stuff.
Thank you.
My experience is that investing in a full Bayesian approach pays off, particularly if there are decisions to be made at high stake, where if you know that you're uncertain, it pays off to collect more data, right? Which might be reformulating the question or something, fearing hallucination. The active learning is a nice general way of benefiting for this. Have you seen in the set of benchmarks other cases where this particular value of the Bayesian approach can be demonstrated and tested and compared?
Yeah, I think what we showed with the... Okay. Yeah, so here, when we see the Bayesian methods have higher predictive uncertainty when they're less overconfident. But overall, I agree with you that to me, the value of uncertainty comes in decision making. That's why I really hope that Bayesian LoRa will be useful for these agentic models, because those are really huge LLMs, but also they're going to be making decisions at every time step about what to do next.
There was the next. Mike is coming. Yeah.
Nice talk. I was just curious about, is it possible to extend the kinds of out of distribution shifts that you do in the package that you have? Like if I want to do something other than just Gaussian noise, is that something you're thinking about?
Yeah, definitely. Even when I was doing the Gaussian noise, I was like, I hope there's no computer vision people in the audience, because they'll always say Gaussian noise is not actually realistic noise. Like in medical imaging, the kind of noise you care about is never Gaussian. So I would need to talk to someone who, but yeah, it should be pretty easy to implement that in principle. But I don't actually know what kind of noise appears in medical imaging. So if anyone knows, come to my poster and tell me.
Okay, good. And we have time for one more question there.
Yeah, thank you for the talk.
Thank you.
You mentioned predictive uncertainty. I assume you mean total uncertainty here, especially because you have a Bayesian model which you can then disentangle the uncertainty into aleatoric and epistemic. I was wondering if you have tried anything regarding that.
No, I haven't. I guess the Bayesian, the sort of posterior stuff is usually getting at epistemic uncertainty. But yeah, I think in principle it should be possible to disentangle them, but I haven't looked into that yet, but that'd be interesting to look into.
Okay, good. Let's thank Colin again.